Morning, class. I'm going to start in a few seconds here while we wait for a few people to join in. Okay, so let's get started. As always, I'd like to start with just a few reminders of things that are coming your way. Homework 3 will be released today after class, and this is going to be a different homework. It's not going to involve any programming. It's going to be entirely on Canvas. It's due in 1 week. Um, it'll have a similar um, structure as homework 0, in the sense that there'll be multiple choice questions, and the goal of this homework is really to kind of revisit what we have covered so far, so that it gives you an opportunity to go over what we have seen so far, rather than just getting lost in the details. So this homework is multiple choice, but the tricky part here is more than one answer may be right. So you actually have to think about all the options. And you get 2 attempts, just like homework 1. The mechanics are essentially similar to homework 1. Sorry, homework 0. It's very similar to homework 0 in that sense. Um, just like homework 0, this is not timed. You just get to spend as long as you want, and you go over it once, and if you make any mistakes, it will tell you which questions you got wrong so that you can revisit them. The point of this homework, as I said, is to kind of get you to think about what you have seen so far and reflect on it, so that we can use that as a launchpad for going ahead. There'll be at least one more homework of this kind. It'll be like a checkpoint of, okay, what have we done so far? That's one set of things. This should be available on Canvas sometime, I think, right after class or towards the end of class today. The other thing is about a project milestone that's approaching. This is going to be on October 20th, and for this milestone, you should have submitted at least one non-dummy submission on Kaggle. What that means is you need to have downloaded the data, done some pre-processing if necessary, some feature extraction if necessary. Note that the project is a little bit more open-ended than your homework. You get to do what you want with the data, subject to the rules of the project, which are listed in quite a bit of detail on Canvas. So by a non-dummy submission, I mean you need to have run a learning algorithm on the data and submit the predictions to Kaggle. But this may seem like a lot of work, but you can think of this as an opportunity to revisit the code you have from your homeworks so far. Or if you found that your code was not working and you wanted more time and you wanted to kind of fix things, this can be another opportunity for you to revisit that for that reason. In addition to that, you need to submit a small report on Canvas, sorry. This report need not be more than 1 page. It could be like maybe a paragraph or two that just says, what have you done so far with the data? And what kind of what algorithm did you run? What were the results that you got? How did you do cross validation, etc.? And any descriptive statistics. Here's the majority label. Anything that's interesting. The point of this is for you to kind of have a free form exploration of the data. At the very least, for example, you need to say what's the majority error, for example, and such things. And at the same, the procedure for this milestone is you need to make a submission on Kaggle, see where it stands, or what accuracy it gives you, and then write a report. Already, I've noticed people have started making submissions, and at this point, the highest leaderboard accuracy is about close to 80%. I haven't looked at what algorithms those are, but if previous experience is anything to go by, this record might not stand for too long. And this is a new data set for me as well. I haven't played with it myself, other than some early explorations. So I'm also curious to see how far it can go. So are there any questions about the homework or about the projects? Oh, my PA just reminded me. Um, there are a few technical things about the project that I should remind you about. Uh, First of all, you're not allowed to use any for 5. You need to make, by the end of the semester, you need to have made at least 5 submissions on Kaggle. Sorry, at least 6 submissions on Kaggle. 5 of those should come from code that you wrote. You should not be using a machine learning library. The 6th one, you are allowed to use um, some machine learning library if you want. You're not required to. So don't use library submissions for this run, mostly because this will kind of, it's a suggestion. Try to get your own code working, mostly because that will get your other runs also. It'll set you up nicely for future submissions. That's one set of things. The other thing is, for algorithms that we cover in this class, I expect that you should be able to implement them. So don't use library submissions, for example, for perceptron. That's I expect that by the end of the semester, you should be able to implement a whole bunch of learning algorithms, perceptron and decision trees being one of them. So there are a few other comments on Canvas, on the chat. There are so many platforms here. We have Canvas, Kaggle, and the chat, and I have a Slack window. So it's a bit of an attention uh, problem here. So there is a couple of comments on the chat. Something is still locked on Canvas. I think the project thing will get unlocked on Thursday. You can make your submission by then and get your report going and all that if you want to get it done. And the homework will be unlocked right after class. For the perceptron, what if one example in the test set has a higher dimension than what was trained? This is an interesting question. Let me kind of elaborate on this question, because it comes up often and it's an interesting thought exercise. So the question was, let's say there is your training set consists of an x1, x2. I'm not writing the labels. Let's say your training set has only 3 examples: x1, x2, x3, and this is say I'm not writing the bias feature either. So let's say this one is 10, 3, one is -3, 5, and this one is 4, 7, something like this. I'm just making numbers up. Now you train your classifier on this, and you get a weight vector which is something like W1, W2, and you get a bias. And now you want to take this and apply it to a test example. Let's call that X4. But you find that X4 has a feature that never appeared in the training set. So X4 has something like 3, 6, and 1. Now, at this point, this seems like a weird thing, right? So maybe there was this feature in the test set that never shows up during training. And how do you even proceed? Let's think about this. This particular feature is an extra dimension. And now I could ask you, what value did that feature take during training? So during training, that feature never showed up. Or equivalently, as Anthony mentioned in the chat, equivalently, that feature took the value 0. If that feature took the value 0, remember, how does the perceptron update work? It's always W is W plus RYX. You're always adding YX. So in particular for W3 is W3 plus RYX3. Oh, I've used up X3, but you know what I mean. That particular dimension keeps getting 0 added all the time. What that means is W3 is 0. So this weight is equivalent to 0, which means this feature will not contribute. Or another way of saying the same thing is, if a feature never shows up during training, its weight is going to be 0, which means you can safely ignore it. Right? Now, that's the default case. If there is anything else that's going to happen, then you need to have a good reason for it. There may be situations where such features may be useful, and I encourage you to think about that. But this is the default case. If a feature never shows up during training, it is essentially uninformative about the label, because that particular feature has not told your classifier what the label could be. As a result, that feature is not going to contribute to the final decision, even at test time. That's a good question, and it's an interesting puzzle. Maybe this is a kind of question that I would love to put in an exam at some point. Okay, so there's another question. Are there different variations for the project? Are the different variations of perceptrons counted as separate types, or should we use the best perceptron type as your final submission? So this is I have been going back and forth on this, and as far as I'm concerned, I'm going to say think of the perceptrons as one type. At the end of the semester, when you're maybe trying to think of other algorithms to implement, I might give you suggestions, and maybe I'll say, okay, fine, let's say I'll use a variant of a perceptron as a different type. But for now, think of all the perceptrons as one type, because we will encounter enough learning algorithms that you may not want to just play with the perceptron alone. So think of all the variants of perceptron as one type. So think, when I say different algorithms, let's say different families of algorithms. In particular, one useful tool that will come your way is this notion of an ensemble, where you're not building one classifier, but a committee of classifiers that together make a decision. And you can kind of play with ensembles to invent new kinds of algorithms. Okay, there's another question. Are we allowed to do feature transformations in the project? In fact, yes, you are allowed to do feature transformations in the project, absolutely. I would say there's some rule involving, in the rules, there's some rule involving features. You should use at least 2 different feature sets. I have given you, I think, 3 different pieces of information. There is some sort of word embedding, there's some sort of bags of words, 3 or 4 actually. And then there's also additional features that are demographic type information. Remember, the task involves predicting whether, based on a transcript of a court session that took place in London a century or so ago, based on the transcript, was there a guilty or a not guilty verdict? In addition to features from the transcript itself, I've also provided information about the case, like the demographics of the defendant, the victim, and so on, the age and such things. So you can use those features. You are required to use 2 sources of information, namely, maybe one could be, say, some sort of bag of words features, and the other one could be the demographics, or one could be bag of words, the other one could be word embedding features. Play with 2 sources of features. And I just remembered that as part of the project rules, you're supposed to try out at least 4 different algorithms, not 5. The reason is you can use the same algorithm with 2 different features, just to see how it works, for example. So at least 4 different algorithms. At most, one of them can be from one of the 6 can be from a library, and at least 2 different sources of features. These are the rules. And if you want to get done with your project and don't want to leave it all the way to the end of the semester, you can, as we see homeworks and you implement new algorithms, just run it on your project also and make a submission, see what happens. This will give you some sort of this will give you essentially what you have is this extra data set that's with you through the semester for you to throw algorithms at, or any ideas at. Another question. In the last homework, we increased the feature space using the product, and we were able to improve the accuracy using that. With an unknown data set, how would we be able to know that an increased feature space would help? That's a good question. You try. This is where this is interesting. There is, for any sort of a learning algorithm. So despite what you might see in the news, or at least the news, if you read the kind of news that I do, machine learning is not magic. So there is actually a certain amount of design that's involved in this. The design includes things like deciding the hypothesis space, which is saying, should I use, say, a linear classifier, or should I use something else? The design also includes the learning algorithm. Maybe you want to train a linear classifier, but you should use a perceptron or SVM. That's not going to, as we will see much as we go along, that's a slightly less sensitive thing. Your performance might not depend so much on that. The design also includes what features you should use and how these features should be transformed if necessary. Now, technically speaking, the right way of answering all these design choices is to do something like cross-validation over the cross product of all these choices. So for this design, for this set of features, for this hypothesis space, for this learning algorithm, for these hyperparameters for this learning algorithm, you get the cross-validation accuracy. And you try that everywhere. But um, of course, if you're going to try every possible combination in your cross-validation, you're going to run out of time. So sometimes you just make some choices based on uh, if you want to be charitable, you can say domain knowledge. If you want to be uncharitable, you could say wild guesses. Um, Something involving what you understand from the problem. Sometimes, and unfortunately, sometimes you might just be given a data set with no information about what the data means. You're just given a bunch of vectors and said, go learn. In those situations, you just have to brute force or just guess or do what you can. Unfortunately, those things happen quite a bit. But in an ideal world, if you're going to be a machine learning engineer somewhere, you would have to um, think about the provenance of the data. What is the data? Where is it coming from? What does it mean? What do the features mean? And maybe think about that. So a few other questions. For the project, are we competing to get the best accuracy? Will the runtime be taken into account? So you're not competing. The competition is, so I used to call this the competitive project, and maybe that word has also snuck in some um, something I've written somewhere. But I don't. The competition part is mostly to keep you engaged. It is fun to get on top of a leaderboard. It's just that's pretty much all where the competition ends. Um, so the don't who is at the top of the leaderboard will not affect what score you get. That's one thing. The second thing, however, if let's say that I'm going to implement a bunch of algorithms on the data set, I already have run a few different things. And if your accuracy for that particular algorithm is way off from mine, then you will lose points. So you have to tell me which algorithm you use. It's essentially similar to the homework. You should not be too far off from what is expected in the for that algorithm. Will the runtime be taken into account? Mm, Not really. I mean, the runtime will not be taken into account. You'll be writing reports for your project. You will have to submit your code at the end of the semester, and I will try to run your code if there's something fishy. I'll skim through your code and I'll run your code only if something doesn't add up. Um, the runtime will not be taken into account. I don't think the runtime is measured, but I'm curious to know the runtime. So if you actually do, if you are finding the runtime, do document it. Most of these algorithms should not take too long. So um, this is not a massive data set. At no point in your code, in your in this class, will we be using a data set that would count as massive by, say, industry standards. We won't have a data set with a million examples. Um, there was a time when I used to give a data set with 100,000 features, but the complaints from the students could be heard across the city. So I'm probably not going to do that unless I feel like I want to challenge you more. But you will not have to have it should not take too long. And there's a subjective thing about what does too long mean. For example, in some cases you have um, like in the wild, for example, when you're working with data sets, I've had situations where classifiers are trained for days, if not weeks. And by that measure, a few minutes or 15 minutes is not too long. So the last question before we move on to the lecture for today, will it be sufficient to justify some of these design decisions as domain knowledge in our report? I would like to understand a bit more. Um, uh, I'd like to understand what made you think about this. I mean, yeah, sure, you can one possible thing is I wanted, so domain knowledge means that you know something. I would like to understand what it is. Um, so, or alternatively, it's perfectly okay if you say that I wanted to try out, say, quadratic features. So I tried it, I did cross-validation. Here is the cross-validation result for that. It was better, the cross-validation accuracy was better than not using the feature transformation. That's why I'm choosing to go with this transformation. Rather than saying, I've tried this, here's the result. I want you to try it, perform an experiment to see if this trial is good, and based on the result of that experiment, move on. So this is where machine learning becomes an empirical science. There is a lot of virtual lab work here because we are trying out ideas, and these probes may succeed or fail, and you choose to continue based on that. All right, so let's move on from extremely empirical things to a little bit more theory. This might be the most theoretical part of the class. Starting today and for a couple of weeks at least, we'll be talking about computational learning theory. Computational learning theory represents the theory of generalization. You can think of this as the beginnings of the laws of nature when it comes to learning or learnability. So just before we get into the details, I wanted to kind of make sure that we are all on the same page. So we've seen supervised learning. We're still talking about supervised learning. We've seen this notion of instances and concepts and hypotheses. And the general model that we worked with at least with batch learning, is you're given a big bucket of labeled data. It's thrown into a learning algorithm. Different learning algorithms do different things, but all of them emit a hypothesis, or we can call this a model, H. Now, once we have a model, the hypothesis is really a function. It can take new examples and make predictions. Under this model, we've under this framework, we've looked at specific algorithms. We've looked at decision trees, the ID3 algorithm, and we've looked at perceptron, and we've looked at variants of perceptron. So many different variants, and you've implemented both of these things. In addition, we've also looked at some important general machine learning ideas that maybe transcend these specific learning algorithms. We've looked at this notion of features or instances, both of them, as high dimensional vectors. The dimensionality of the data set or the dimensionality of the problem becomes an important complexity parameter that we will be playing with as we go along. We touched upon this notion of overfitting, and we'll expand on that a bit more as we go along today, or in the next couple of lectures at least. And the overarching structure that frames the entire semester is we keep asking the question, can my problem be learned? And we look at different answers for that. We've already looked at one answer for that, which is the mistake bound model, where we said I consider my problem as learnable if there exists some learning algorithm that can make only a polynomial number of mistakes in the dimensionality of the problem. If that happens, we will call that a mistake bound concept. We'll call the concept or the problem learnable under the mistake bound model. We looked at this sort of a proof of concept algorithm, the halving algorithm, that says, yeah, mistake bound algorithms can exist. Halving is a pretty inefficient algorithm, but it just says there exists at least one mistake bound algorithm if you don't care about efficiency. And then we looked at the perceptron algorithm, which is actually a practical mistake bound algorithm, at least the online version of it. The online version of the perceptron is a practical mistake bound algorithm that says if your problem has certain properties, it can be learned with only a finite number of mistakes. The mistake bound for perceptron being r square over gamma square. So are there any questions before we launch off from here? We will keep seeing this big picture slide every now and then, mostly to make sure that you don't get lost in the details. This class talks about so many different things that I feel like it's worth coming back to the surface for oxygen every now and then. So let's this unit about computational learning theory is going to cover a fairly broad array of topics. Today, we'll talk about the theory of generalization and what kinds of what kind of attributes this theory might have. And time permitting, we'll also look at the definition of something called probably approximately correct learning. Once we look at the definition, just like the definition of mistake bound, this definition says certain concept is learnable under this framework if certain properties hold. And using the definition, we will try to prove a general theorem that we will call Occam's razor that talks about whether certain things are learnable or not. And using the Occam's razor theorem, we'll look at certain positive and negative learnability results. That theorem will tell us this concept class is not learnable, this concept class can be learned. And we'll move on to, we'll keep relaxing the assumptions we made in these results to move to this notion called agnostic learning, where we are working with a hypothesis space that may not even contain the true concept. How close can we get to the true concept? And then we'll talk about this really cool notion of shattering and VC dimension, which allows us to generalize this theory to infinite dimensional, to hypothesis spaces that are infinite or uncountable but have real numbers in them. So all of this is going to occupy us for the next at least couple of weeks. I hope it will get done at least in the next couple of weeks. Let's start off this deep dive with an exploration of what the theory of generalization might look like. So, as I said, computational learning theory involves answering the question, are there general laws of nature related to learnability? This is a somewhat profound concept. Learnability, the ability to learn something, seems like a very human thing, or it seems like a very animate thing. So, but then there are a few different constraints in place. When we think about what does learning mean, there is of course information being transferred from nature to the learner. So is there enough information in the communication that the learner can actually pick up the concept? If there isn't, learning is not possible. Or if a concept is so complicated that it requires a ton of information to be provided, learning is extremely hard. Similarly, is there enough time for the learner to actually successfully complete learning? This is the computational complexity argument. Is there, will there be enough time? The time complexity of learning, is it reasonable? Is it polynomial? Now, what we want from such a theory is we want the theory to connect a collection of things that exist with respect to learning. The probability of successful learning. Can learning succeed or not? How many examples do you need? The number of training examples. What's the complexity of the hypothesis space? Like, if it's are we exploring more complex functions or simpler functions? How accurate do you want your classifier to be? So if I don't care about accuracy, maybe learning is going to be easier. If I'm okay, if you give me a classifier that's like, 51% accuracy for a balanced problem, maybe you can do that without requiring too many examples. And the other question is, how are examples presented to the learner? We've talked about this before, so we won't touch upon this right now. The online learning versus active learning versus batch learning and so on. What we want from computational learning theory, from the field, is we want a theory or theories that can relate all these things so that we can know, is this problem learnable? With this hypothesis space, with these many examples, if I care about this much accuracy. So with this end, let's maybe talk about this last point. How are examples presented? We talked about a few different things, and I'm not going to revisit this point in detail, but these are slides you've already seen. We care about how good is, suppose we care about how good is a learning algorithm. And we are learning this conjunction F, which is hidden from the learner. F is X2 and X3 and X4 and X5 and X100. We are in the batch mode of learning, which means nature gives us a bunch of examples that are labeled. Each line here represents one example. which is an assignment to the 100 bits. So let's say we have 100 bits here, x1 to x100. So each line corresponds to an assignment to the 100 bits and a label. And let's say the learner also is aware that the true concept is a conjunction. What the learner can do is, knowing that it's a conjunction, the only examples where the output can be 1 are where all the features that are relevant are present. So you only look at those examples and take the intersection of all the features that are present in those examples. So we see that x2 is present in all the 1 examples. So x2 is present in the final function. x100 is present in all the 1 examples. So x100 is present here, and so on. So clearly you'll find all these things, but it turns out here we also have x1 that's present everywhere. So x1 also shows up here. This algorithm, we call this elimination. So whenever the output's 1, x1 is present. And so a reasonable learning algorithm will say that, there's no way I can rule out, there's no way I can eliminate x1, because whenever the label is true, x1's present. So it seems like x1's present. So then the question is, with only this data that we have, we've learned only an approximation of the true function. The true function does not have x1 here, whereas the learned function, h, has x1. So is this good enough? This is the question we need to answer, right? We will not necessarily always learn the true function. So the question that we have to think about is, given a function that we have learned, is this good? Now, with this framework in mind, with this perspective in mind, we can answer this question in different ways. There are at least 2 different directions. I can think of at least 3, but we'll talk about 2. We can analyze this probabilistic intuition. I never saw x1 in any positive example. Imagine instead of these 9 examples, we had 9 million examples, and we never saw x1 equals 0 in any positive example. Maybe it just doesn't happen. Maybe x1 is a feature that is just correlated with one of the true features. So it just shows up. So we don't have to worry about it. So if even, let's say it's not perfectly correlated, even if it actually shows up as 1, it is so rare that the concepts we learn are going to be pretty good. It's going to have reasonably good accuracy, because this is such a rare event. We will not make that mistake of x1 making the label wrong. And by pretty good, the important thing is its generalization. It's not pretty good on the training set, it's pretty good on future examples. If you analyze this sort of a frame, if you continue this line of thinking, you will arrive at the PAC framework, which we are going to do now. Another way of thinking about it is we can think about mistake-driven learning, where this learner keeps updating its hypothesis, and we say, there's no notion of an absolute good or bad in this case. It's just good means I stop making mistakes. If I can prove that I will stop making mistakes somehow because of this algorithm, then I don't care how it gets there. Instead of stopping making mistakes, you can say my accuracy would be good enough in a certain way of thinking. And once again, this sort of online algorithms are another. The word model is overused. In this case, there's the online model and the batch model. Think of it as the framework for thinking about learning. In the online model, good enough is defined in a certain way. In the batch model, good enough is defined in terms of performance on future examples. So we've already talked about the mistake-bound model. It's a theoretical framework. We may be able to determine for certain classes of functions what's the number of mistakes a learning algorithm can make before converging. The mistake-bound model it's a simple model for learning. When I say model, as I said, it's a framework for learning, for describing learning, but it does not tell us how many examples do I need before arriving upon a good hypothesis. It only says you'll stop making mistakes. For example, let's say that there's a problem where my mistake bound is 10. It's a small number. So I tell you that I have this concept and a certain learning algorithm that's only going to make 10 mistakes. but I'll not tell you when those 10 mistakes are. It might actually show up at an inconvenient time. Imagine a self-driving car that is only going to kill 2 people. That seems like a really awful self-driving car. So this is a this is the kind of thing that this is the weakness to the mistake-bound model. We don't know when these mistakes will happen. So we would rather, for example, for the self-driving car, these mistakes happen in a simulation rather than in real life, but we can't tell. That's because the strength and the weakness of the mistake-bound model lies in its lack of assumptions about the order in which training examples are presented, or about the distribution of the examples. What's the probability that this example will show up or that example will show up? In PAC Learning, in our analysis of PAC Learning, we'll spend a lot of time talking about distributions over training examples. And that's what's going to give us something extra. PAC Learning is a model for batch learning. The learning protocol looks like this. We have a fixed training set. We train a classifier on this fixed training set, and then we deploy it on future examples. We don't get to revisit we can keep the training set in mind, but we don't usually do. But it's not like examples are coming in one order during training. We get to control the order in which the algorithm sees the examples. The way in which we define success is how well will our learning algorithm do in all the future examples? What's the probability of error in the future? So with this sort of a high-level introduction, let me just start formalizing this process. So we have an instance space. We'll call this X. It's a set of examples that exist, can exist, and have existed. So think of it as a set of all possible emails that can ever be written. There is a concept space, C. C is a set of possible target functions. There's one element of C that we are after, F. F is the hidden target function. C is a set that you can think of it as nature uses C to choose the true concept. We don't even know what C is. We can make assumptions about it, but this is a useful theoretical thing to keep in mind. It's a set of all possible target functions, of which one of them, F, is a special function that has actually labeled examples. This C could be so complex that it includes the noise in the data, for example. We can make assumptions about C. We can, for example, pretend that we know that nature only uses n conjunction or all n-dimensional linear functions, for example. What we do get to decide is the hypothesis space, H. It's a set of all hypotheses, or it's a set of all functions that our learning algorithm is going to explore in order to find this function F. H and C need not be the same because we don't even know C. But for the time being, we'll assume that they are the same. Now, given these things, we are given a training set. The training set is a set of examples that are labeled. So it's a set of pairs. It's from S cross -1, 1. We are working with binary classification. So each example consists of, oh, this is a mistake. It's not S. Yeah, sure, this is technically fine, but each example consists of an instance with an application of the true function on it. We have x1 and f of x1, x2 and f of x2, and so on. We have, let's say, n examples. The goal is we want to find a hypothesis H inside our hypothesis space such that f of x equals h of x. Okay, that's the goal of learning. And now a question for you to think about is, do we want H to be equal to F on all examples in S in the training set, or on all examples in capital X, the instance space? I've launched a poll. You can kind of vote on this. And while you're voting, you can ask me questions. Yes, the goal is still generalization. That's right. The goal is always generalization. So X is the set of example. X is the instance space, and C. So C is the set of functions that the learner is choosing from. Sorry, that Oracle is choosing from, and H is the set of functions that the learner is choosing from. We hope that H is a superset of C, so that every element of C shows up in H, but that we can't be guaranteed. Like, for example, take your project. The classifier, the true classifier that was used to decide whether a person is guilty or not guilty, depends on so much more. The concept class is, in some sense, a view into the mind of nature. We don't get to pick that. We just hope we get a good enough approximation using H. In an ideal world, H will contain C or even be equal to C. But in real life, we don't even know what C is, so it's just a best guess. So I think many of you have voted about. So I'm going to end the poll, and a majority of you have said that the hypothesis, you want the hypothesis to be correct on all examples in the instance space. But let me revisit this point. I need to show the results. Yes. So the X, imagine that X is the instance space. S is a set of examples that inside the space, I'll be using this sort of a two-dimensional metaphor quite a bit today. So instead of writing it this way, X is a set of examples that you have some pluses, some minuses, something like this. It's a finite set of points. And our goal is we already know the labels for those points. What we want is the labels for all these points where we do not know the label, because that's the goal of generalization. We have the training set. We already know the label. For example, if you're given an email and I tell you that this email goes into the work folder and not the personal folder, you already know the label for that email. The goal of generalization is to learn the lessons from that particular email and apply it to a future email that has not yet been written, or to an email for which you do not know the labels. So the goal of generalization is for your hypothesis space to do well on examples that are unseen rather than examples that are seen. So there's a question, can I give an example of C and H and show the difference between them? Sure. So C is, for example, as a simple example, you can think of, let me pretend that we can read the mind of nature and say that we have some, I'll use decision trees as an example here. So let's say we have a data set X with, let's say we have examples X1, X2, X3, and so on. And now let's say I am playing the role of nature, and I have decided that each example here is going to be labeled using some sort of let's say a decision tree of depth 15. Now my C is, let's say, all decision tree of depth 15. F is a particular tree. So it's some tree that has depth 15. What I would do in this example, being nature, is I would apply F on all these examples, and this is F of X1, this is F of X2, of X3, and so on. But let's say now you are the learner. You don't get to see this. This part is hidden from you. What you need to do now is use this data that you only get to see these examples. So your goal is to use this data and learn the function, but you don't know that I'm using decision trees of depth 15 or even this particular function. So what you do then is you make an assumption. You assume that, yeah, this is the data that I have, and I'm going to use linear classifiers to find this true function. So notice that I am using one set of functions to label the data, and you're using perhaps a different set of functions to discover the function that I have. And if you're very lucky, you might actually find the function, or you might find a close approximation. For example, if you use as your H could be all linear classifiers. Then in terms of the functions, so these functions just look different, but both these functions, linear classifiers and decision trees, take examples and provide labels, right? So they do the same, they have the same interface. So you can think of C and H to be sets. So you have a concept class C, and you have a hypothesis class. In this case, the hypothesis class is actually smaller. So this maybe is all dt, and this is all linear. It's contained inside that. So maybe if I use this function to label the points, you will not find it. Another possibility is this is the, let me be consistent with the colors. So this is C and this is H. So you could use, this could be the concept class, all linear, or let's say all decision trees of depth 2, and your hypothesis, your learner is searching over all decision trees of all possible depths. So it contains the thing. So then you will, if I use any function that I use inside this, you will find it because you're searching a larger space. In a very, very lucky case, H will be equal to C. Does that, given this example, answer your question? Or at least give an intuition? The important thing is C is not known. C is just a sort of a conceptual thing that we will find useful as we go along. For now, for the purposes of at least today and Tuesday's lecture, assume that H equals C, but we will drop that assumption as we go along. So going back to the thing, what we want is a hypothesis that is good on all future examples. But asking for a hypothesis that's good on all future examples is such a difficult thing because there are an exponentially, if not infinitely large number of future examples. How could we possibly know that this hypothesis is good on all future examples? It seems like a good thing to want, but how do we do that? Instead, we make an assumption. We assume that the training examples are generated from a fixed but unknown probability distribution over the instance space. This distribution is something we will call D. There is some distribution, D, that generates examples. We may not know it, but what we do assume about it is it's fixed and it won't change. Future examples, it's not just the training set that's generated from this distribution, all examples are generated from this distribution. So the future examples will have the same probability of showing up as the training set examples. All training set examples are generated independently and are all identically sampled. So they are IIT. So this idea of training examples being generated from some distribution has, people tend to find that a little bit problematic. So let me give you sort of a cartoon example. Imagine that we have a two-dimensional instance space. So we have two features. Let's say we have x1 and we have x2, two features that are at play. And now, not all points in the space are equally likely to show up. And the reason for that is this is just an abstract space of features. Maybe some features are more likely to be generated by the process that generates examples. For example, think of sequences of words. Not all sequences of words constitute an email. Not every sequence of letters is a name, right? So some names are more common. Some sequences of emails are more common. In other words, there is a probability that for any point in the space, there's a certain probability that it exists. We don't know what the probability is. We don't even know what shape that distribution would take, but there is some distribution. That distribution will be called D. It may look something like this, for example. It essentially says that points in this region and this region are more likely to show up. Points in this region are basically not going to show up at all. If you prefer a contour plot instead, it may look something like this. So these regions are extremely improbable. Here, points are extremely probable. These points are also somewhat more probable. So you're essentially drawing points from this probability landscape. And now the question is, how do we get a training set? A training set is generated using this distribution. What that means is points are sampled from this distribution. We are not doing the sampling. Nature does the sampling for us. We don't have to worry about how the sampling happens, but points are sampled from this distribution according to give us our training set, a finite set of samples drawn from this distribution. So this distribution, we'll call this D. We may not know that this is the important point. We may not know what the distribution is. In fact, it might take an extremely complicated shape. It might be so complicated that we don't have the tools to even sample from it. But nature, thankfully, takes care of it. And what we do assume is this distribution is fixed. Not only are training examples sampled from this distribution, future examples are also taken from this thing. So this fixed but potentially unknown distribution assumption is going to be the key assumption that we are going to use in pretty much all our analysis of learning as we go along. And this is what is this assumption forms the backbone of PAC Learning, the theory. This assumption may not be always true. The probability distribution over, say, names changes based on when in time you are. It changes based on where you are. So it's not a fixed distribution. The probability distribution of emails changes over time. So it's not a valid assumption in life, but it's a convenient assumption that allows us to analyze learning. The intuition, this assumption is an important assumption because it gives us a few conceptual tools. It gives us hope that what we learn on the training set will actually be relevant for the future. Because if you're learning on these examples here, and I tell you that you'll be tested on points from here, there's no point of learning because maybe the way the concept behaves in this region is very different from the way the concept behaves in this region and this region. So if you're going to learn from points of high probability according to this distribution and you're tested somewhere else, how could you possibly generalize? So this fixed distribution assumption gives us hope for the training, that the training data is actually meaningful. The other thing it gives us from a practical point of view, it gives us a formal definition we will see in a minute for the notion of error according to a target function. A somewhat loose way of thinking of this assumption is the future will be like the past. We've seen many examples. This is what the assumption tells us. We've seen many examples that are drawn according to this distribution. As a result, the future will also behave like these examples that we've seen. In the example that in the case study that we saw with conjunctions, in all positive examples, X1 was active. It's very likely that X1 will also be active in positive examples in the future. If it turns out it doesn't happen, this is such a small fraction of examples because they are so improbable, especially if your training set is large, it is so improbable that our error will be small. Intuitively, if examples show up from this region of the space, they are so rare that even if our classifier makes some mistakes on it, it will be only in a few cases. This is the assumption that we will use to bound the notion of error when we perform our analysis. So let's just to move on a bit, I want to talk a little bit about error, but and then come back to this, open it up for questions. I said that the fixed distribution assumption allows us to write down a definition of error. Given a hypothesis and given this distribution, we may not know this distribution, but at least we can name it. So if we have a distribution D, we are going to define the error of the hypothesis as the probability according to this distribution of the function of the prediction h of x not being equal to the ground truth. The probability. So notice that this thing inside the bracket is essentially that saying that an error has happened. The event here is the classifier is wrong. H of x is not equal to f of x. The error of a hypothesis is the probability of this event happening. This thing is called true error. It's also called the generalization error. And sometimes it's just the unqualified error. If you want an intuition here, suppose again we have this two-dimensional instance space. I'm not showing the distribution. Suppose we have this instance space, and let's say the target concept labels all the points inside the circle as positive. So this is the target concept. And now let's say we have learned an approximation of this function. The function that we have learned is labeling all points inside this this shape as positive. There are for all points inside this intersection, the target concept is correct. The error is really the weight of these two regions, where the true concept, the true function f, and the hypothesis disagree. But you can think of this as the area of this function, but it's really the volume according to the probability distribution. If let's say this region is extremely improbable, even though it may have a large area, it's not going to matter. This is the true error. This is the generalization error. Another kind of error that we will encounter is the empirical error. The empirical error is something we can actually compute. The true error depends on the distribution. It's not something we can compute. It's a theoretical concept. We don't know the distribution. It's a fixed but unknown distribution. So we can't, in pretty much all cases, compute the generalization error. Empirical error is something we can actually compute. I'll call that error S. Error S is simply the fraction of examples in the training, in the set S, where F and H disagree. So it's this is what you've been computing in your code also, right? Given a set of examples, what fraction of examples do they disagree? So we have two notions of error. We have error D of a hypothesis and error S of a hypothesis. Error D is the generalization error or the true error, and error S is the empirical error. Now, suppose you're given a certain training set, S, and we find that the training error is substantially, well, we can't find it because we don't know. But suppose somebody tells you that the training error is substantially lower than the generalization error. This is an example of overfitting. Essentially, what's happened is that the classifier that we've learned, this H, remembers the training set really well. So well that it cannot actually do well, it cannot perform accurately on the future examples, on the true set of, on the true distribution over the examples. When this happens, we call it overfitting. We've already seen overfitting before, but this is like a slightly more formal introduction with all the assumptions that go into this definition. Are there any questions about this notion of distribution, about this notion of true error or overfitting, and so on? There is a question, what's underfitting? Underfitting is a different scenario. Underfitting is where even the training error is so bad, and the test error and the generalization error. Sometimes I know that I will make this thing, so I'll also say it. Sometimes I call this also the test error. The test error, this is not exactly correct, but I tend to make that slip. So I'm just letting you know. Underfitting is when the training error and the generalization error are both low. It just means that the hypothesis class is not expressive enough. We are working with a set of functions that are not rich enough to capture the true concept. We'll talk about underfitting much later. What do we say when the training error is much, much more? So error S of H is more than error D of H. Now, this is, I would say this is a strange scenario. Um, this would mean that, oh, actually, hold on. Uh, so that means that the training accuracy is, yeah, this is a strange scenario. This is like this very odd and extremely fortunate situation where we have a training set, we have a classifier that's doing really awfully on the training set, but somehow magically it's doing fantastically in the future. I would call that a remarkable coincidence, a potential bug. So something worth examining in detail. Are there other questions about this thing? Is there any formal way to achieve? So that's the question. Is there any formal way in which we can compute the error D? Remember, error D depends on the true distribution. How could we possibly know? So there's a suggestion. Do people look at the distribution of error? Oh, actually, that's a different question. So um, the error D requires us to know D, but how? We don't even know D. How could we know what the true error will be? And the answer is what that's really the rest of the mandate for computational learning theory. Looking only at error S and something about the hypothesis space, can we say something about error D? Can we bound how bad could error D be if error S is less than something? And this is what we will actually be examining in a fair amount of detail. There is a formal, uh, if you're willing to agree with all the assumptions that we will be putting in place for proving these theorems will essentially be telling us that error D will be bounded in certain ways. And this is to answer, to kind of wrap up that answer to your question, Mehdi, we will be looking at these things starting Thursday. So the other question is, do people look at the distribution of error? The distribution of error is actually a very interesting thing, and I think we should look at it more than we do. The distribution of error will tell us, are there any sampling issues, for example? Are there any stability issues? One way of looking, for example, at the distribution of error is to use something like cross-validation. The variance of accuracy the standard deviation of the accuracy behaves like the distribution of the error. So I think people look at it less than they do. My personal opinion is we should look at it more. So let's go back and revisit what are the goals of batch learning. Our goal is to devise learning algorithms that avoid overfitting, where overfitting is this thing here. In other words, we want to find functions. We want to invent learning algorithms that are not fooled by functions, that are not fooled by classifiers, that only appear to be good because they explain the training set so well, and just by accident, or just by remembering the training set. So the goal of batch learning is to invent learning algorithms that avoid this. So we've seen two notions of learning, online and batch learning, and I want to compare and contrast them. In online learning, there's no assumption about the distribution of examples. In fact, we make a worst case assumption. No assumption means worst case. The examples could be constructed in a way that we are only presented with bad examples, and we want to still do well in that situation. In batch learning, we assume that the examples are drawn from a fixed, but perhaps unknown distribution over the instance space. In online learning, learning is a sequence of trials. In fact, there are some people who think of online learning as a collection of games. In each trial, the learner sees an example and then makes a prediction. After it makes the prediction, then it gets the opportunity, if necessary, to make an update. And then this example gets thrown out. In batch learning, the learner is not seeing an example one at a time. It assumes that the training examples are drawn IID from the distribution that's there. IID is short for independent and identically distributed. Independent because each example is sampled into your training set independently of all the other examples. Identically distributed because all examples are drawn from this same distribution D. So in batch learning, we assume that the training set is an IID draw from this distribution. In online learning, or at least in the mistake bound variant of online learning, the goal is to bound the total number of mistakes over time. In batch learning, the goal is to find a hypothesis that has a low probability of making a future example. But what does it mean, low probability? It means that we want to find a hypothesis that has a low probability of making a future example, provided that example is also drawn from this distribution D, because it's a fixed distribution over the instance space. So are there any questions about this, what we've seen so far? Earlier, I mentioned that a training set could be drawn adversarially. No, I said that in online learning, the examples could be drawn adversarially. Here, the training set cannot be drawn adversarially. We don't get to control that. It's an IID draw from the fixed distribution. Will we consider any learning algorithms where we don't treat D as fixed? Unfortunately, because of time constraints, we will not be looking at that. We will, so if you want, we can talk about that offline. This does happen. So both F and D could change over time. So the domain could change over time. The concept could change over time. And we will not look at algorithms for that, but typically the way one sort of a pragmatic way in which you can handle that is you keep updating your training set. And essentially, you keep sampling new examples, and then you keep improving your learning, the model as time goes along. A very boring way of doing that is, let's say I collect a training set every day, and at the end of every month I train a new classifier on the last month's data. Automatically, that will be current, so to speak. Another way of the essential, but then that assumes that we are throwing away old examples. So you can think of updating. And now we are coming to this sort of a mix of online and batch, where we are updating examples based on recent things. So we won't be looking at algorithms that do that, but that, as you can imagine, would present problems, because as we will see, this fixed and unknown the idea of a fixed distribution is going to be a key tool that we will use for proving theorems, and the theory gets tossed out once we assume D is not fixed. Could the learner pick the samples? Yes, that's where active learning comes in. Active learning is essentially saying the learner picks a sample and says, I want a label for that. And active learning always tends, not always, but often tends to be very effective. Active learning has other issues, but at least it tends to be information effective. It tends to ask for, if well implemented, if the learner truly exposes its uncertainty to nature, then it can choose to ask questions where it will be able to get the right example to make it better. So active learning tends to do a good job when, for example, concept moves around. In fact, this notion of a fixed and unknown distribution has other unintended complications. For example, even though it is fixed, it might be biased. It might be, say, geographically biased. It might be biased temporally. Maybe imagine I'm using the data that you have for your class project and using that to decide on court cases that are happening today in the US. It makes no sense, because even though there is a fixed, if we assume that there's a fixed and unknown distribution of trials, that doesn't really add up, because trials happening in the United States today are very different from trials that happened in UK 150 years ago. So there are, we are not going to that assumption is something that we will use quite a bit, but you always have to worry about whether that assumption is true when you are looking at data. Final question. So the three protocols are online, batch, and active. Actually, there are more. Online and batch are the ones that we are looking at in a fair amount of detail. There's active learning, there's reinforcement learning, there is learning with some sort of weak supervision. There are multiple kinds of protocols. Reinforcement learning is is something that we don't have time to cover at all, but if you're interested in that, I think the AI class or maybe one of the robotics classes covers that. So what we are doing right now is batch learning. What we will be doing going ahead is batch learning. All right, so in the 10 minutes that are left, I want to kind of set the stage for just defining PAC learning. PAC stands for probably, approximately correct learning. So just to kind of revisit the setup, we have an instance space. This is just a summary of all the notation we have seen so far. We have an instance space and a label space. D is an unknown distribution over examples. F is an unknown target function. The function maps instances to labels. It comes from a concept class C. H is a hypothesis class that the learning algorithm is exploring. And the goal of the learner is to find an approximation of the concept F, which we will call H, little h. To do this, we have a set S consisting of M training examples that are drawn from this distribution D. And then once these examples are drawn, the target function labels all of them. There is the true error, error D of the hypothesis, and there's the training error or the empirical error or the observed error, error S of the same function. These are all the objects that these are all the things that we have named so far. The goal we want is related to one of the questions that came up. Can we say something about the true error, knowing that the empirical error is something? Is a certain concept class C even learnable? Is it possible to learn C using only functions inside the hypothesis class H? Is it possible to learn it using the supervised protocol with batch learning? How many examples do we need to guarantee good performance, whatever good means? All of these questions, we are going to try to kind of develop a theory that answers many of these questions, or at least ties together these questions in a certain way. The thing to keep in mind is we need to have reasonable expectations of what learning is. We cannot expect a learner to learn a concept exactly. Typically, given a certain finite data set, there will be multiple functions that are all consistent with the data set, because the finite number of examples are a small fraction of the instance space. This was a point that we observed even in like the first week of class, where we are only shown a few rows of the truth table. There are many functions that are going to be consistent. In the worst case, the unseen examples could have any label because we don't see them. So if an example is extremely rare, or if an example of a certain type is extremely rare, we should probably agree that we might make mistakes on it. And we will agree to make mistakes. We can't be perfect. We will, let's say that we'll get a classifier that's close to good. In fact, this, unfortunately, in some hopefully only rare situations, we may not even be able to get such a close approximation of the true function, because maybe we got really, really unlucky with the training set, and it's just not representative. If our choice of not our choice, the training set we are given is so unrepresentative that there's no hope that we're going to learn the true function, then we may not even get this true approximation that we were agreeing that we will live with. So we may not be able to learn a concept exactly, so we can live with an error, and we may not even get a close approximation in some unfortunate cases. So the only realistic expectation of learning is, with high probability, we will be able to learn a true close approximation. So there is a question. Would a poor, yes, so rare diseases, for example, are would be a good example where we may not get a close approximation of rare disease. So actually, these uncommon examples you can think of them as rare diseases. Imagine that, okay, that's a good set of examples. Let's say that imagine we have a classifier that looks at, say, some sort of the vitals of a person and predicts what disease they have, whether they are ill or not. Binary classification. And in order to train this classifier, of course, we are not going to be able to get a perfect classifier, because if there's a rare disease, we probably will have to have a human in the loop, let's say. So the system might make mistakes. Now, if, for example, that particular classifier was trained using only rare diseases by some quirk of nature, in other words, the training set is not representative. In that case, the classifier that you trained only using rare diseases will actually make mistakes on common diseases. A majority of examples would be common diseases, and the classifier would make mistakes. So if we are so unlucky, I mean, this seems like a weird definition of unlucky, but if we are so unlucky that we only get a data set with rare diseases, then the classifier will make mistakes on common diseases. So we would not even have a classifier that's a close approximation. So the only reasonable expectation that we can hope for is, with high probability, we would like a classifier that's a close approximation. So in other words, we are willing to live with approximate correctness, but we are willing to even relax that by saying we want a classifier that's probably approximately correct. With high probability, it's approximately correct. This notion gives us a formal definition of PAC learning. In PAC learning, we will pick up on this on Thursday, but I'll just set up the stage for the definition. In PAC learning, in the definition, we are given these two parameters, epsilon and delta. Epsilon is how much error are we willing to tolerate, and delta is what's the probability that learning itself will fail. So what we want is, with probability at least 1 minus delta, we get a classifier that produces an error of no more than epsilon. With probability at least 1 minus delta. If delta is really small, that means with high probability, that's what we have here, we hope a learner produces a classifier with error that's small, error that's no more than epsilon. If this happens, then we will declare something to be PAC learner. We'll see a formal definition of this on Thursday, but the intuition is important to kind of get. We cannot hope for a perfect classifier. We cannot hope to always find even a good classifier. So what we hope is, often we will find a good enough classifier. Often means with high probability, with probability 1 minus delta, learning will succeed. We'll find a good classifier. What does good mean? We'll define good not as perfect, but not as perfect, but as something that has an error no more than epsilon. And we will see that the only reason we can hope that this agenda even makes sense is this consistent distribution, this fixed but unknown distribution assumption. All right, so I have a minute left, so I'll probably not go into the formal definition of PAC learnability. We'll start with that on Thursday, but let's see if there are questions. There's one. How high is high and how close is close? There is high and close. Both of these are defined by epsilon and delta. It depends on the application. In some applications, an epsilon of, say, 0.1 might be okay. Epsilon equals 0.1 means the error is 10%. Maybe in some examples, that's okay. In some cases, an epsilon of 0.0001 is still not acceptable. It depends on the application. It depends on the context in which the machine learning system is going to get used. Similarly, delta. In some cases, it's not going to be acceptable that learning will fail. Let's say delta is 0.1. That means in 10% of, if you run this algorithm on 10 different data sets, learning will, on 100 different data sets, in 10 of them, you will find a bad classifier. Maybe that's unacceptable. Maybe for your, in your context, you want a probability of success to be very small. Sorry, to be very high. So all of this then it depends on what you want in the domain, and it's going to be like dependent on what the domain demands. So we are a minute over time, so I'm not going to answer that question. Can you still learn if the sample distribution isn't consistent with the real distribution? Answer is learning becomes very hard. We'll pick up on this on Thursday, and we will look at the formal definition of PAC. I'll stop now. I have office hours in 15 minutes. If you want to chat about this or the project or any homework, feel free to come by. Otherwise, I'll see you all on Thursday.